Here's the third video of chapter 13. So we just talked about molarity. Now we're looking at another way of calculating concentration, which is molality. Very similar word, but molality versus molarity. Molality uses this small little cursive M, and what it equals is moles of solute over kilograms of solvent. This is very specific. Has to be moles of just the solute on top and kilograms of just the solvent on the bottom. So the units can either be moles per kilogram, but more often we use just a little cursive M for the units, which we could say molal. So to make a 0.150 molal solution of sodium chloride, how many grams of sodium chloride should be dissolved in 500 grams of water? So we've got our molality here, that was given. I know that it's equal to moles of solute over kilograms of solvent. I might have said that wrong. Moles of solute over kilograms solvent. So I don't know how much solute is dissolved, but I do know that I had 500 grams of water. So I'm going to convert that to kilograms by dividing by 1,000. That'll give me my kilograms down here. We'll cross multiply to get to moles of solute, which comes out to be 0.0750 moles of sodium chloride. Once I get to moles, I can then find grams. If I'm ever asked to find grams, sometimes that's not in the equation, but if I can get to moles, then I can hop over to grams. So I use my molar mass from the periodic table, multiply by that, and it gives me the grams of sodium chloride. We also will be given percent sometimes as our starting point. So let's see what to do here. It says, what is the molality of a 10% solution of aqueous sodium chloride? What I always recommend is if I have 10% solution, I break it down as if I have 100 grams of total solution. Because if I have 100 grams of solution, it means it's 10 grams of the solution is the solute. So there must be 10 grams of sodium chloride dissolved in the 100 grams of solution, because that would be 10% of the solution. What I then have to remember is that the solution down here is made up of both the solute and the solvent. So if I know that 10 grams are sodium chloride, then there must be 90 grams of water. Okay, now I have a breakdown of my solute, which is 10 grams, and my solvent, which is 90 grams. So what I can then do is focus. I'm trying to find molality. So what I need to come up with is moles of solute and kilograms of solvent. So I go focus on my sodium chloride, which is my solute, and I need to get it to moles. So 10 grams of sodium chloride. I would use my molar mass from the periodic table. Go grams to moles. Here's my moles of sodium chloride. So now I know the top number. Then I need kilograms of solvent. So I'll take my grams of water. I'll divide by 1,000 to get kilograms. And I get 0.090 kilograms. And here, just scribble this part out. That right there shouldn't be there. The 100 grams to 0.100 kilograms. That would be total. But we don't want total. We want just the kilograms of solvent, which is the 0.090. So we divide here, and we get 1.9 molal. So that is the correct molality of this solution. Here, a solution is made by dissolving 4.35 grams of glucose in 25 milliliters of water. Calculate the molality. So I like to just always remind myself, what is molality? So what am I looking for? Well, I've got to figure out moles of my solute, and I've got to figure out kilograms of solvent. It's kind of two different pieces. So if I go focus on my solute first, which is the glucose, I can easily go grams to moles using the periodic table and get to my moles of solute. So that's what I do, 4.35 grams, divide by the molar mass of glucose, and here's my moles. So that's going to go on the top of my molality over here. Then secondly, I need to get my kilograms of solvent. Well, 25 mils of water is the same thing as 25 grams because of density. I divide by 1,000 and I get 0.0250 kilograms. That's going to be my denominator. So I can divide and get the 0.966 molality. So when we're talking about solutions, there are certain properties that change when you dissolve solute into solutions. And these are called colligative properties. They depend on the number of solute particles, meaning the more solute particles you dump in there, the greater these properties change. And the four that we will run through are vapor pressure, boiling point, melting point, which remember melting point and freezing point are the same, and osmotic pressure. These changes only depend on the number of the solute particles, not the identity. So the more ions or the more particles present, the greater the change. So we have to understand this little I value, which is called the von Hoff factor. What it's telling us is just when a substance is dissolved, how many particles are you getting? So really it comes back to, are you a strong, weak, or non-electrolyte? Okay, so here if you've got glucose, he's all nonmetals, so he's a non-electrolyte. So for each of these compounds, you're going to get one particle because he's not breaking up any further. So the I is 1. It's just telling you you are getting one compound for every one compound. NaCl is ionic, so he's a strong electrolyte. So you just look how many ions are here. Well, there's one Na and there's one Cl. So every time a compound gets dissolved, you will get 2 particles. So I is 2. You kind of get more bang for your buck there. K2SO4, also ionic, so therefore strong electrolyte. He will actually produce 3 ions because you're going to get 2 potassium ions and 1 sulfate. So you're getting 3 particles for every compound. And then ammonium phosphate, he's also ionic, 2 polyatomic ions. He's a strong electrolyte, will break up. You get 3 ammoniums and 1 phosphate, so you get I equals 4. So we'll just have to use that multiple times as we go through these. Let's focus first on what's called vapor pressure. We've talked a little bit about vapor pressure. Remember, it's the pressure that a liquid is exerting upwards. So as we add solute particles, I've written it down here, as you add more solute particles, you reduce the vapor pressure, which means as there's more particles dissolved, there's less of an upward force, okay? So we reduce vapor pressure. The way we can calculate vapor pressure of a solution is using Raoult's law here. And what this is the PA is the pressure, the vapor pressure of a solution is equal to the mole fraction of the solvent times the original vapor pressure of the solvent. So this is really important here with this mole fraction because it's unusual. You want the mole fraction of the solvent, meaning you're going to put moles of solvent like water up top over total moles, salt and water, whatever it is in there. And then multiply it by the original vapor pressure of the solvent. I'll show you an example here. Calculate the vapor pressure of water above a solution that has 22.5 grams of lactose in 200 grams of water. And it tells me vapor pressure for normal water is 187.5 torr. So I've got to figure out mole fraction, and I'm already given the original pressure, which was 187.5. So really I've just got to focus on mole fraction, and I've got to get moles of my solvent over my total moles. So really I need to find moles of lactose and I need to find moles of water first. So lactose, there's 22.5 grams. I go to the periodic table, add it up to find the molar mass, divide by that, and here's my moles of solute. Do the same with water. I change it from grams to moles using the periodic table. And then for my mole fraction, I've written it here. We're going to put moles of my water on top because that's the solvent, over total moles, which is the 2 added together. And then I take that fraction and multiply it by the original pressure. So it's always going to be a fraction of that original pressure. Now this one didn't go down very much because there wasn't very much lactose for the amount of water. But you do notice that the pressure went down from 187.5 to 186.4. Boiling point and freezing point. These two kind of go hand in hand because you calculate them similarly. What we know to be true is as soon as you add solute particles to a solution, your boiling point is going to go up and your freezing point is going to go down. So I just think of a thermometer like this. Boiling point is going to go up, freezing point go down. So if you have plain water, it will boil at 100 degrees. If you have plain water, and that's Celsius, and water will freeze at 0 degrees Celsius. As soon as I add any salt or any solute, water's going to boil at a higher temperature now and freeze at a lower temperature. This is called boiling point elevation and freezing point depression. You calculate the change very similarly for both. You'll see the equations here. The change in boiling point is equal to a boiling point constant times molality, so little m, molality, times the von Hoff factor, which is that I value. Delta TF, the change in freezing point, is equal to a freezing point constant times molality again, times little I for von Hoff factor. Somewhat conceptually, let's look at this example here. Which aqueous solution will have the lowest freezing point? Well, think about this. The more solute particles you have, the lower the freezing point will go. So here, if we are calculating each of these being put in water, for example, here's my equation. The KF is going to be the same for every single one because they're all going into water because it's aqueous. So KF will be a constant value here. So really what I'm trying to compare is what is the molality and how many particles are you getting. So I'm just going to do M times I so that I can compare these scenarios. Calcium chloride, the molality is given, and I is 3 because you're going to get 3 ions. So I get a 0.15. For sodium chloride, I've got 0.15 as my molality. My I is equal to 2 because he's going to break into 2 pieces, and I get 0.30. Hydrochloric acid, he's a strong acid, so he's a strong electrolyte. I've got 0.1 molality, and he's going to break into 2 ions for an I of 2, and we get a 0.20 value. This is actually acetic acid. He's a weak acid. What we would say about weak is, remember, only 5% break up, so I'm going to actually treat him like a non-electrolyte because he's mostly going to stay intact. So I'm going to take 0.05 times 1 and get 0.05. And then lastly here, this is sucrose. He's all non-metals, which means he's a non-electrolyte. The I value is 1, and the molality is 0.2. Then you just see who has the greatest MI here, and that will be NaCl in this scenario. So B would change the freezing point the most. He would have the lowest freezing point. If you think about who would have the highest freezing point, meaning who would change it the least, D would change it the least because it's the smallest number that you got. So it would change the freezing point by very little. Here we see an example of how to actually calculate the new boiling point and the new freezing point. So in both scenarios, we've got these 2 equations. The change in boiling point is given here, the change in freezing point given here. Well, KB and KF are given to me, 0.51 and 1.86. The I values are easy because it tells me that both of them it's a non-electrolyte. So my I is a 1 value for both. So really I've just got to go find my molality for each. Well, if it's a 25% solution, remember we're going to assume that we have 100 grams of solution. If we do, then there's 25 grams that is made up of the antifreeze, the actual solute. And then I also have to remember that the solution down here contains the solute and the solvent. So I break it up and I know 25 grams is the antifreeze and 75 grams must be the water. So I focus first on my solute and I need to get it grams to moles. So I go to my periodic table, I convert grams to moles so that I know moles of solute. And then remember molality, which is what I'm trying to get right now, is moles per kilogram of solvent. So here's my moles that I just found. There's 75 grams of water in my scenario. So I change that to kilograms and put it on the bottom. So moles of solute over kilograms of, or moles of solute over kilograms of solvent. I divide that out to get my molality. My molality then gets plugged in here into both equations, and I come up with a change in boiling point and a change in freezing point. What it wants me to say though is what is the actual boiling point now and what is the actual freezing point. So what I have to know is that water normally boils at 100 and it will now go up because boiling point elevates. So I add the 2.74 and I get 102.7 degrees as my new boiling point. Water will normally freeze at 0, but it will be depressed and go down by 9.99. So the new freezing point of water here, or not of water, but of the solution, will be negative 9.99. So it doesn't freeze at 0, but it freezes at close to negative 10 degrees Celsius.